Okay, now the talk for engineer Sameh Zaghloul. Sameh Zaghloul is a CTO and digital transformation leader at Fixed Solutions Group. He also specialized in architecting complex enterprise scale solutions, and his talk today about quantum risk assessment. I am really interested to know about quantum risk assessment.
Assalamu alaikum. Actually, this session actually is complementary to the risk part, actually, the opposite of quantum computing. Okay, so it is coming. Okay, so we need to be prepared. This is actually the main point. So what we are discussing today actually is quantum safe future, simply assessing quantum risks, current and the future. Future, you know all about future risks actually, but what about current actually? We know actually. This is not only happening currently, actually it started happening a couple of years so far. And the transition, this is the challenge actually. This is a complex migration project for critical infrastructure. So this is a very complex migration for infrastructure. Okay. Briefly, what is that three side of quantum security triangle actually? Okay, let's imagine that we have our data actually stored in this vault, say. Okay, in order to keep my data safe, actually, we need three things, and this is actually the three sides of quantum security. First part of how truly random generated keys I use in my encrypting the data. So this is we call true random number generating, which we can use quantum technology on it. So first one actually is to use real random keys. This is the first one. Mandatory actually now actually and 20, 30 years ago. So this is mandatory in all cryptographic system. True randomness. The second part, this is related to the evolving power of quantum computing is to use post-quantum resistant cryptographic algorithm. So instead of RSA and yes, and all famous algorithms that we all use in our own application currently as we speak, in this live streaming actually use RSA for example. Okay, we need to migrate this actually to another category of algorithms actually that theoretically, quote unquote, should resist quantum computing at the Q day. The third important part is quantum communication or quantum key distribution. This is the sessions that already Dr. Salim Hajjaj actually talked about. Okay, I need actually to secure the transmission of the keys actually. This uses quantum technology. Okay, this is sorted by difficulty actually. This is the most complex part, but this is the future of quantum security actually. Quantum key distribution or quantum communication or quantum cryptography. Okay, but this need dedicated actually quantum hardware, like using photonic chips actually, like Dr. Salim was mentioning today. The second part, this is post-quantum cryptography actually migrating to post-quantum algorithms actually. This does not need quantum hardware. This should be done as the only way to be done actually in our classical system now. So this can be started actually immediately today, yesterday, 2 years ago. Okay, so we don't need anything actually to start implementing this. And the easiest one is to use a true random number generator or quantum random number generators. And this is commercially available. Personally, I know at least 10 companies worldwide actually produce this quantum random number generator hardware. And this is something we can produce in Egypt, by the way. This is something like ASIC chip, but photonic. It does only one thing, actually, it generates a continuous random sequence of photons. That's it. But this is very easy to manufacture. No. And this is what we can start with. So this is to summarize actually the 6 things that we need to have a complete security. Okay. Q day. This is actually coming within few years. Okay. This is the time actually when the power and qubit count of quantum computers actually will be enough to break Shor's algorithm for RSAs that already developed 30 years ago, or the equivalent algorithm developed, I guess, something like less than 1 year. So we have actually, since last October, the equivalent for Shor algorithm for ES. So actually, all algorithms are there, just needing actually the right power. We call it the cryptography relevant quantum computer. Okay, and this is not new news. Actually, this is published by at least 10 years now by NIST. The type of affected algorithms. Actually, this is published 9 years now. And this is a problem statement that we are talking about. Okay, there is a theorem, very nice theorem, Mosca theorem, x plus y. If x plus y greater than z, actually, then we have a problem. X is the migration time of my critical systems. Okay, y actually is the life shelf actually of the data that I'm protecting. And Z actually is the here. So if I exceeded this, actually, so my data is exposed. But this is in the Q day. Does this mean that we are secure for now? Let's see. But before we go to the migration, actually, this will not happen for the first time. Why? Because we have been there before many times, actually, since the start of cryptography in 70s. At least there was something like 8 migration milestones actually for cryptographic algorithms migration. So this happened many times before. This is migrating for post-quantum cryptography. Actually, this is not something new. Actually, okay. The impact will be a little bit larger or huge, but this happened before. Actually, at least 10 times actually through the journey since 70s. Okay. So again, we are talking about transition to a new family of cryptographic algorithms or cryptographic security. Okay, and we need to do it now. One important point, okay, regarding post-quantum cryptography algorithm, and this is actually this comment was mentioned by Dr. Ahmed Yunus many times before. Okay, this is work in progress because we have a standard coming from US NIST FIPS 203, 204, 205. Okay, this was published, I guess, less than 1 year. And this is equivalent, actually, a work actually done in the European Union and equivalent work done in China. Okay, of course, work done in China is not published, of course, for sure, for many reasons. Okay, one of the reasons, actually, one of the published reasons that they will not use any quantum cryptography standard from US or Europe because they are not sure actually it is really secure or not, which is valid. Okay. The other important thing actually is this, and this will relate to something called what we call cryptographic agility. That okay, if next year actually we have modified version of FIPS 203-1 or -2 or -3, actually, what I should do. So I need actually to migrate to an agile system such that any new cryptographic algorithm actually could be plug and play without redoing hard migration once more. Okay. I'll start with threat actor, not today, but Q day. Okay. This will happen in Q day. This is what we expect to happen. Okay. The threat actor, okay, will get the encryption keys and will get the encryption data, and using quantum computing with enough power actually can already decrypt the keys and the data and access my data. Okay, this is clear. Okay, what about today? This is a threat actor today actually. Actually, not today. Actually, this is at least 3 to 5 years because the term harvest now, decrypt later started to appear actually 4 or 5 years ago. So this is what is currently happening worldwide. The threat actor, okay, is capturing encrypted keys and encrypted data. Can he already decrypt them now? No. Okay. He just stores them and will decrypt them later at the Q day. What does this mean? Okay. If my data will be valuable or critical after 5 years, assuming that Q day is 5 years. Okay. So someone has my data now, okay, and can decrypt it 5 years ahead. This is risk. Okay. If my data actually, shelf life of data actually is more than that 10 years, for example. So it's the Q days 10 years, so it's the same actually. If my data actually is shelf life actually 1 year, so I don't need to worry. And this is part of quantum risk assessment. So part of assessing all the criticality of this is assessing the criticality of my data and the shelf life. And this brings us back actually to most critical actually. The migration time, which is not trivial. This is a huge effort, and the shelf life of data. This plus this, and this is the time actually to Q day. In other words, actually, what I tried to say actually is everyone in the world actually is doing this on the other countries, either countries, organizations. Okay, so actually this is started actually, and we are at risk since few years now. So when we need to take action, as a Q day, yeah. After the Q day plus 3 years. Exactly. Okay. So what we mean by quantum risk assessment, and we need actually to build what we call cryptographic inventory. Okay. I must know actually what cryptographic inventory I'm using in my system. Okay. Then also the PKI health check. My PKI infrastructure, the systems that I generate my keys actually, private keys and public keys. PKI, our certificate authority. Okay. And also actually we need to do post-quantum risk assessment. Risk assessment actually, what is the value of this data? What is the criticality of the breach? So I put the plan and the roadmap actually based on risk and cost. This is the risk assessment mainly actually. So we start with immediate fixes actually and short, and also work on the long term. Okay. We have many of classical encryption algorithms actually in all the layers of the system: symmetric, asymmetric application, hash functions, key exchange protocols, digital signature, and all the cipher keys that we are used, and all the cryptographic libraries actually that we use currently. One good thing actually related to open source. One of the advantage of the open source currently is almost 99% of open source stacks in all applications without exception, like OpenSSL and OpenVPN, has migrated already to post-quantum algorithms actually since something like 1 to 2 years before. So already. يعني actually the next competition was running like 5-6 years now, and there is multiple candidates. Many times, yes, this is exactly the cryptographic agility. So actually, I have OpenSSL version 1.x, okay? And version 2, actually, we had 2 years ago, the first version of post-quantum cryptographic algorithms. And every couple of months, actually, we have a new version with the enhanced protocol. Exactly. And this is exactly what we mean by cryptographic agility. I don't need to migrate everything from scratch. This will be just as normal upgrade. The challenge is to do this actually for complex systems. This is not an easy task, believe me, actually. Okay. So what is the order of magnitude actually? What is the effort, the level of effort actually that we should expect here? For example, if we take a medium-sized data center, HVM or Docker instance or whatever, or server, will have typically from 20 to 50 distinct cryptographic algorithms with different flavors from the previous slide actually. So I can have 5 or 6 versions of RSA in different layers of system. So this will not be considered one. This will be counted as 5 actually, because I need to handle each one separately. So if we have actually in the medium data center, I'm talking a large enterprise with critical data, 100 servers, actually you are talking about hundreds of cryptographic algorithms. So first part actually is to know what I have and inspect all the layer of the system and get a detailed inventory. There is no one tool actually can do this automatically. No, I need to use mix of tools because we have starting from the user layer application, a web layer, application server, middleware, integration service bus, API layer, database, operating system, networking, storage, all this layer actually, the 7 layers, the classical 7 layers. I need to actually to check each layer thoroughly, and also the code. So multiple tools must be used in this, from static code analysis, dynamic analysis, runtime applications, and network traffic analysis, which is very, very important. Okay. Configuration system scanning on all levels, okay, for system handling, and dependency analysis, which system call what systems, and also cloud environment scanning, either public or private, and hardware and firmware analysis. This is very important, including servers, storage, network, firewalls, IPSs, everything. I need to check the firmware actually for all my devices in all categories, and also certificate and key management. This is very important, and the log analytics like SOC solutions and so. So it is not an easy task, but it is not impossible. Okay, this is take a lot of effort and multiple teams actually, because the main challenge here actually when we started this services or this exercise, that we need multiple skills actually: network team, system operation team, infrastructure team, security team, application team. Okay, combine the team actually to gather all this information. The target is to build what we call cryptographic bill of material. Cryptographic bill of material is simply some standardized form actually. It is open source, and by the way, actually historically it was both open source by IBM actually a couple of years ago. Many organizations use it in collecting actually, or this is de facto scheme actually for collecting cryptographic data. Okay, so CBOM actually is our target. This is actually in a one inventory system. I need everything: system, application, IoT devices, all the devices actually in one layer application. And we have a holistic overview of my cryptographic landscape, mainly for enabling risk management actually. So I need to track this cryptographic inventory at the progress done on each step. Okay, and review our readiness. There is no standards actually put currently so far, but in Europe, for example, and US as well, they are talking about something like all current cryptographic algorithms cannot be used after 2030. Cannot be used. So, but should I wait to continue using this to 2030? Actually, this is one of the discussions that we need to discuss today, because we read this actually. So I need to stop using this today actually to save money after 2-3 years. Okay. So this is a very simple example for a sample cryptographic bill of material. Something like web server, Nginx, this is open source, very popular. This is the cryptographic algorithm, okay? The library used OpenSSL, which is a good, okay, because actually OpenSSL and TLSL are post-quantum ready now. An example. Back-end API using JWT or Java Web Tokens, okay? This is using RSA, okay? We should prepare actually for using, instead of GWT, PQC GWT, for example. The same for databases, mobile application, cloud authentication system, login services. The main thing here, actually, we started doing an internal pilot in our systems 3 years ago, okay? So the conclusion actually is that all open source component actually we could immediately, with almost minimal effort, actually migrated to post-quantum cryptography. Commercial components actually still, like for example, I have a firewall from vendor X, or commercial database from vendor Y actually. I am depending on them, unfortunately, because they are not moving that fast, because this need longer cycle of development, testing, deployment. This cycle is much, much faster in open source. So open source actually is one of the recommended strategies actually to be ready for the quantum era. Okay, what we need to do, QD plus 3 years. is hybrid approach, because this cannot be done in 1 week, 1 month, 1 year. Okay, so I need to start with assessing what I have. Okay, and fix the quick actions that I need to implement immediately, and both long term. Okay, and keep continuous monitoring actually for all the components, all the system I installed, like my previous section, actually 1 billion applications. This new application actually at least should be post-quantum ready, just to avoid going in this critical migration path. Okay. One of the examples, quick examples for hybrid approach is data at motion. We have actually data at motion and data at rest. If you notice, actually, actives here actually is focusing currently on data in motion. Okay, transmission over the network. So this is the immediate part I should focus. Okay, data at rest inside my data center storage, so a little bit difficult actually to take the encrypted data from disk, but it is doable. But the immediate risk is to secure data in motion. Okay, and one of the approaches that we already implemented in current 2 projects so far is what we call post-quantum cryptography proxy. So the traffic actually is coming in the application layer. Okay. And already communicating everything using HTTPS and TLS1, okay, and using RSA. This is not post-quantum ready, okay. So what we can do actually is just put a proxy layer on front of my web servers and application layer with post-quantum cryptography enabled, and this will be as umbrella actually surrounding my interaction, my system with the external world. So this is a quick fix and can be actually biased couple of years, by the way, to the final migration. So the hybrid approach is the recommended. The last yes, this is the last slide. Okay, this is mainly actually what we should do in general. This is not a short-term program. No, this is a hybrid, short-term, mid-term, long-term, mainly. Short-term actually is doing the cryptographic inventory and risk assessment. This is a couple of months. Actually, this is a lot of work, but this is not impossible. This is possible, doable, and must be done, because without it, actually, I will not know my risks. And do the quantum risk assessment. Risk assessment, what I should do first, at what cost, at what criticality. This is very important. Okay. Then midterm, like the next couple of months to the end of the year, pilot migration for key systems using hybrid approach, for example. Okay. And then the long term, which is typically a couple of years. So this was in a nutshell, actually, the how to be ready for the risks of quantum computing. Any questions? Okay. Okay. I split it in 2 actually, but okay. One thing about, we are talking about software or middleware, right? Okay. So at least there's okay. By analogy with pen testing, penetration testing, or security assessment. Okay. Yes, exactly. But okay, what we can do? Yes, I'll bring this because this is the reason for this slide actually, the vault and the triangle. Okay, there are 2 things that we can do now immediately without any problem. Okay, first, actually validating the true randomness of the keys. And this is not related to quantum, by the way. This is actually NIST started to talk about this actually like 25 years. So we have NIST special publication 822. This is something like 22 years, something like that. And another one overrided 800 special publication, also 890B, 15 years ago. newer. Okay, so this was actually this set of statistical and the cryptographic tests actually to test the true randomness of my keys. This is doable. It used to be done actually in all critical systems before quantum computing, and we do it now actually on quantum. So this can be done now. No, the keys actually are totally random. This is the first side of the triangle. Okay, the second side I can check actually the used algorithms. Okay, but yes, as you mentioned, I don't have enough power actually to test it. It's really random. That's why actually I put some stress on cryptographic agility and OpenSSL example. Okay, so OpenSSL, for example, is post-quantum ready. Why? Because it uses actually one of the Nest FIPS protocols, right? But am I sure that it is really post-quantum ready? I'll keep testing actually each month, each year actually, okay? And I should be able to upgrade this to the newer version, okay, immediately. So this is, can answer this because yes, I'm not sure. I answer third part actually. This is the part related to quantum key distribution or quantum communication, okay? And this is the topic of Dr. Hisham Badu yesterday and Dr. Salim Hijazi today. This is a little bit tricky, okay? But can be tested, by the way. Yani actually, one of the solutions that provided by the way, China is number one in this area, okay? And everyone in the world actually behind this. But all other solutions in the world actually provide you with simulation key. We call it sometimes Eve simulator, because actually we install the two boxes for quantum key, sender and receiver, or encoder decoder, okay, and a third box actually to simulate intruder or eavesdropper, like Eve, for example, and we can test actually the impact. So this can be tested, but a little bit expensive. So the answer is a little bit can be split to three areas. The second one is post-quantum cryptographic algorithm is work in progress, but we should be ready actually because this is part of life. I hope I could answer. It is a very difficult question, by the way. The second question, sorry. Yeah, quantum key distribution is a special case because the encoder decoder actually should be from the same service provider. Upgrade is the outer layer. يعني the example, for example, the example. Exactly, because this is a critical or tricky migration project. So, by the way, actually, I'm working in IT for many years. A migration project actually is the most complex project, actually, and especially post-quantum cryptography. But I'll start with one example of the proxy layer or the hybrid layer using the web server. So, if I upgraded the web server in one component, actually, I should upgrade it on the other side. So, this must be planned. But this is typical business as usual, actually, for migrating critical systems. The dependencies of the system. So this is business as usual, actually. This is how we do it. It is complex, but it is doable. I hope I can. Thank you very much. I start with only one thing, actually. I'm an engineer, by the way. I work in the field, actually, practical hands-on experience for many years. So I usually, what I learned actually, so put one simple target and achieve it immediately. So I will start with only one thing. All new systems actually should be, will go live actually starting from today, will be post-quantum ready, full stop. There is a 9 items in the list actually, but I'll start with this. No, actually, the remaining actually will be something like this, putting this actually, because this is a very complex. So, for example, Biden has issued a mandate 1 year before he leaves, actually, that all federal government should complete post-quantum readiness assessment. Okay, this did not happen till now, by the way. So, for example, so it is a little bit challenging even for modern countries. Let's call it. So, yes. Yes. So cryptographic agility again actually is one key actually, and this is from my side actually. This is what I see value actually for my background as a solution architect, complex solution architect. If this achieving this cryptographic agility in complex systems, because I'm not talking one component, actually many components integrated and interconnected. Okay, this is good question actually, and let me clarify actually, not necessarily quantum random number generator, but this is actually this is currently available and much faster. Okay, but usually 10-15 years ago, we had what we call hardware called TRNG, True Random Number Generator. What it does, okay, is two things actually, using the pseudo algorithm to generate the keys, and secondly, actually integrate actually external random phenomena like external noise, external humidity, whatever actually list of at least 10, you measure at least 10 random external variables. All of them, you must not have any control of them. And you mix all this actually pseudo algorithm and it's actually random phenomenon actually and produce true random number. Okay, but to make sure you need to apply both statistical entropy tests. Okay, and this actually pseudo random numbers can pass this test, but there is other variant actually. I can actually show after this. Just yesterday actually was talking. Was testing actually something like called Die Harder. Die Harder actually new set of something like 25 statistical algorithms actually was developed actually to overwrite NEST 822 and NEST 890B actually to make sure that okay, this is truly random, will pass the randomness, the chi-square, all this actually, okay, and also cannot be reproduced or predicted. You should not be able to control this. This is the trick. You can measure this to make sure, but the main thing here actually is you should not be able to predict actually what will be generated. This is okay. Monte Carlo distribution actually is one of the statistical tests, okay? But this is not enough, actually. There is something like 20 other tests, actually. I can share with you, actually, after having my laptop, because constantly I was working on this yesterday, because this is part of the project that we are doing. We use quantum random number generator to generate the code, but I must make sure, actually, that the codes actually are truly random. and this is classical problem before quantum computers. Okay. True randomness is totally separate issues, and it is a must actually in all cryptographic solutions.